Hello everybody and welcome to our second lesson on proving triangles congruent. Today our objective is we will be able to use the 5 congruence postulates and theorems as well as coordinate methods such as distance and slope and algebraic methods to prove triangles are congruent. Let's first remember the 5 congruence postulates or theorems that we learned in the last class that help us prove triangles are congruent. I would like you to stop the video right here and write down the names to see if you remember and then compare your answers with mine. Hopefully you came up with the same 5. SSS, ASA, SAS, AAS, and HL. Essentially, another way to think about it is you have all possible combinations of the letters S and A with 3 letters, except for our 2 that we can't use, one of them being AAA because we always need a side, and the other one being the one that spells a bad word, and we don't use bad words in math. And then we also have as the 5th one, our special case, the hypotenuse leg theorem. In this class, we're also going to start being a little more formalistic and structured about how we create our proofs. Well, then let's first talk about what is a proof and how do we want to do this. A very important thing to set up a proof the right way is we have to write everything down. Write everything down. And when I say everything, I mean all the things that are congruent, we have to write down. In other words, what is congruent? And we also have to write down the reasons why those things are congruent. Why is it congruent? And the things that are congruent are essentially our statements and the why is it congruent are our reasons. And we're going to write them down separately in a table, and I'll show you in a little bit how we do this. Let's look at this example first. Complete the following proofs. So first we have something given. The coordinates of 2 triangles are triangle PVH has the 3 points P at -4 and 0, V at -1 and -2, and H at -4, -5. And the triangle NQR has the points N at 0, 0, Q at 2, 3, and R at 5, 0. So the first thing we're going to do is we are going to put our 2 triangles into the coordinate plane. Starting with triangle P, I got point P, -4, 0, V, -1, -2, and H, -4, -5. And I'm going to label my points too, so I don't get confused. And here is my nice triangle. Now let's plot triangle NQR. The point N is at the origin, 0, 0. Q is at 2, 3. And R is at 5, 0. And this is my triangle NQR. We have to prove that triangle PVH is congruent to triangle NQR. So how are we going to do this if we don't have any information given? We just have the triangles in the coordinate plane. Well, we're going to have to do the work ourselves. We're going to have to calculate the side lengths and then compare the two triangles and see if they are indeed congruent. Let's go ahead and do that, and let's start with the easiest side that we have here, the side PH. We just have to count how many steps we go down, so that's actually 5. So PH is equal to 5. Now which side is similar from the looks to PH? I would say that would be NR. So let me count. How long is the distance between N and R? How long is the side? And that's indeed also 5. So PH is equal to 5 and NR is equal to 5. So then we can indeed say segment PH is congruent to segment NR. Okay. Let's move on to our next side. For PV, we can't just go count. We have to use the distance formula or the Pythagorean theorem, since we have the 2 points in the coordinate plane. The side PV always forms the hypotenuse of a right triangle, and the other 2 sides have the length of 2 and 3. So PV is equal to the square root of 3 squared plus 2 squared. In other words, the square root of 9 plus 4, which is 13. Let's look at our green triangle, NQR. Which side seems to be similar to PV? I would say that's got to be NQ. NQ. And using the Pythagorean theorem again, we can say that has to be the square root of 3 squared plus 2 squared, which is indeed the same as we had before, the square root of 13. So this allows us to say that segment PV is also congruent to segment NQ. On to our last side of the triangle, the side VH. And again, we're going to have to use the Pythagorean theorem. The length of VH is the square root of 3 squared plus 3 squared. In other words, the square root of 18. But we did have 9 in there twice, so it's the square root of 2 times 9, or in other words, 3 times the square root of 2. The last side left that we have here is QR. QR is the square root of, again using the Pythagorean theorem, we know that the 2 sides are 3 squared plus 3 squared. Taking the square root of that, square root of 18, we come up again with the same numbers. So it has got to be 3 times the square root of 2. And segments VH and QR are also congruent. So let's mark everything we have found congruent. Segment PH is congruent to segment NR. PH is congruent to NR. Segment PV is congruent to segment NQ. And segment VH is congruent to segment QR. And note that I use 3 different sets of congruence marks. So we found that segments PH and NR are congruent. So that's 2 sides. How did we find that and determine that, by the way? We used the definition of a congruent segment, because congruent segments have the same length. So let's note that down. Definition of congruent segments. Two segments are congruent if they have the same length. PH and NR have the same length, therefore they are congruent. The same goes for segments PV and NQ, so we have another pair of sides that's congruent, and also VH and QR are congruent. So we have three sides that are congruent. Remember, it's usually enough to find three pieces of information if it also relates back to one of our congruence postulates or theorems. We have three congruent sides, so we can now indeed say and have proven that triangle PVH is congruent to triangle NQR. And we have proven this by the side congruence postulate. Okay, now go ahead and watch the second part of this tutorial for a couple of more examples.